Okay, so welcome to the lesson about graphical representation of simple harmonic motion, or SHM, as we call it for a couple of lessons ago. As usual, if I drawing the pictures too fast, or if you want time to try to solve the exercise at the end of these lessons, then you can take a pause and then you start again when you feel you're done, and then you can look at what I've done and see if we have done the same thing. I also would like you to have your calculator beside you now. I will show you how we can draw the graphs on our calculator. Now, I have already told you that if you attach a mass or a bob, as they call it in your physics book, in a spring, and you have it in this direction, and then you pull it down and release it, it starts to oscillate like this. It's moving back and forth. And I have sketched it in 3 different places here what's happening, and I will show you with forces on it to start to answer questions about graphical representations. So in this place, in the middle place here, I can draw a force from the center of the bob or the mass. It's the weight or gravitational force on the mass. Now, this is also the mean place, or the equilibrium. It means that the forces cancel each other out. So the force from the spring has the same size but in the opposite direction, like this. So this is a force from the spring. Let's call it Fs, and they have the equal size. Now, in this case, we have, of course, the same weight. The gravity on this bob is the same as here, so the length of the arrow should be the same. Now let's do it very accurate. So we see now we have 1, 2, 3, 4, 5 squares. So 1, 2, 3, 4, 5 squares down. They have the same size. However, the force from the spring is not that strong as it was here, because the stretch of the spring is smaller here than here. You have stretched it a longer distance, therefore this force is greater than this force. So you see the force upwards is a little bit smaller in this case. So we have a resultant force towards this line. That is the equilibrium line, or the mean position for the mass. In this case, the force downwards is still 5 squares. 1, 2, 3, 4, and 5. So the weight or the gravity force is the same, but in this case, the force from the spring is bigger than the force from the gravity. Therefore, in this case, it will accelerate towards the equilibrium line. So it oscillates. It's going down by the conservation of the momentum. It keeps on going here, and then the force upwards becomes greater than the downwards force, and it goes back again, and then it starts going back and forth like this. So I have start drawing a diagram like this. So we have the timeline and we have the displacement. So if I pull it down and release it, it starts to go up, and in some situation it is here. So this coordinate represents these points here, the same height. And this is a point where it's at the mean or equilibrium, and then it's at its lowest point here. So let's see, 1, 2, 3, 4. 1, 2, 3, 4. That is that point. 1, 2, 3, 4. And at its lowest point. So you can draw it something like this. And you see this beautiful sinus curve. Okay, we have talked about that the displacement, the maximum displacement, is called the amplitude. So you have the displacement capital A here, the amplitude. It's a distance and you measure it in meter. We also talked about the time period. It represented by capital T. It's the time for one complete oscillation like this. You could also measure the time from the top to the next top. It's also a complete oscillation like this. And we have the word for angular frequency also. Angular frequency, or omega, we defined it as 2 pi divided by t, or 2 pi f. We have to know it now. Because if you want to describe this curve as a function, we said it was a sine function. So the displacement x can be written like this. It depends on the amplitude, and then you have the sine function for omega times t. Like this. I will use my calculator to show you this now. So let's take the calculator and see if it's true that the sine function has this wave look-alike. You start it, and first of all now we will use radians. So press mode, and then we go down to radians, not degree. We have to differentiate this, and then we really need radians. Enter. And now we press y equals 2, and I would like to write this, but we have to choose some values on A and F to be able to do that. So in this case, let's choose A equals to 5. It could be 5 meters or 5 centimeters, doesn't matter. And F is equal to 1. Okay. Then, oops, something has happened here. Now I have to turn away this. Sorry, in equals, quit in equals, and now it wasn't gone. No, let me see. No, it's transform, yes. Transform, uninstall, and now this is gone. Okay, so let's see. A, the amplitude, let's call it 5. And you multiply it. You don't have to have this multiplication. It understands it anyway. And sine for omega, that's 2 pi times f. Now f is 1, so that is very easy. It's 2, and pi, you have it in blue here. So blue, and this one, 2 pi times 1, don't see it. And then we multiply it with the time, but now it's x here on our calculator. We could end with the brackets if we want to. Now I press zoom, and then we go down to trigonometry. So it choose a window for it. Let's see how it looks. Like this, and we hardly don't see it's a sine function. So let's go to window again. And here I will choose to start from 0, exactly like I've done it here. Start from 0. And then I go down one step, and x max, I choose 2. It's okay with that. Y min, I choose negative 30. And Y max, I choose 30. I will show you why later on. And then we press graph. And then we see a curve like this. It starts origin, it goes up, it goes down and up a couple of times here. Okay, so it feels like it's probably the right equation to describe the graph like this. Okay, now let's derivate or differentiate this function. If I do that, I call it x dot like this. It's the differentiate according to a time. Then you have dot instead of prim. And that is the same thing as the velocity. The change in displacement in a certain time is the velocity. So I have to differentiate this function. And if I do that, you've done it in maths, so you know it will be the amplitude times the derivative for this, that's omega, times cos for omega t, like this. Let's see what that means for our velocity when we draw this function. I will draw it at the same time as I have this. So I go into y equals 2. I go down one step and then I will write this. So a is 5. And then I will multiply with omega. Now omega is 2 pi times 1. So 2 pi. And then times cos instead. The derivative function for sine is cos. Cos, and then the same thing here. 2 pi times the time. That's x. And then let's draw the graph. So it looks like this. Now, if I would just sketch it here. So, you know, at the same time as we have the displacement on the y-axis, we also now will have the velocity. Velocity as the time goes by. So, you see, it starts at the y-axis and at its top, and then it goes down. Now the scale, it doesn't matter which it is, so I just start somewhere here like this. Let me see if I can do this for hand. It will go something like this. Now, why is it likely to be in that way? Well, first of all, as we have the displacement here, that means it is in the middle, then the speed is the greatest. In this case, it's going upwards, so it's going upwards and it has the maximum speed. And then it starts to decrease. The speed is decreasing. So at this point, it's at its highest point. It's in this case. Here, it's standing still. Because it has reached its maximum point and then it will go down. But it stands still here. And you can see that right below the maximum height at the amplitude, the velocity is 0. And then, well, it's going down then, and then we have this point, and we have the 0 point here. This point, it should be written like the bob is here, and then it's going up first. So this is like the starting point when it's going up. Then it reaches its highest point, it's standing still. then it's going down again, and it's here. So the displacement is 0, but it has a great speed downwards. Therefore, it's negative. And then it continues going downwards, and then it stands still here. So here it's standing still, and we can see it on the velocity graph. The velocity is 0. But the displacement is at its maximum. And then it starts moving upwards again. So the speed is increasing, and it's reached the highest speed as it's at the mean position or equilibrium on this line, So it seems like it's true. You can see it here as well. Maximum speed, the minimum displacement. The maximum displacement, the lowest speed, well, the speed is 0. Then it has the highest negative speed when it's going downwards. And at its lowest point, the speed is 0 again. And so it continues back and forth. From maths, you know something else. You know what the gradient is. So let's look on the gradient for this line. The gradient, or the slope, you can find it by draw the tangent here. And you see the tangent here, it's the gradient for this pen. It has a quite high value. So if I would plot the gradient, it would be quite high. But the tangent in this point is 0. Therefore, the velocity is 0. In this point, the tangent is negative. Therefore, the velocity is negative. In this point, the tangent is 0. Therefore, the velocity is 0. And then the tangent becomes positive more and more, and the velocity increases more and more until the gradient is at its maximum. Therefore, the velocity is at its maximum. So it makes sense. We understand this. If I differentiate one more time, I have the second derivative, or the first derivative according to the velocity. That is the acceleration. And if I differentiate this once more time, I have to differentiate according to on cos, so it becomes the negative sine function. You remember that from maths. And then we will have the same amplitude, we will have omega, and we will differentiate the inner function as well, so it becomes omega squared. And then we have sine for omega t. Now, let's see. Sine omega t, we have it here as well. And we have the amplitude as well. So the amplitude times sine omega, that's the displacement. So we can also write this as negative omega 2 times the displacement. So we see that the acceleration is proportional to the displacement. That means the higher the displacement, the higher the acceleration. So we have the maximum acceleration here, because then the resultant force is the greatest. And we have the highest acceleration here as the displacement as it is highest. But the opposite acceleration, it's towards the equilibrium all the time. Okay, now we have to look at an example on this. So, turn page. And here you have the example. You can write it down, you can take a pause. And when you have done it, you can try to solve the problem. And when you have solved the problem, then you can look and see if I would do at the same thing as you do. Okay. Oh, sorry. You need to have the question first. So, describe the displacement time relationship with an equation. Okay, so a mass on a spring is oscillating with a time period 4 seconds and amplitude 8 centimeters. 4 seconds for the time period. Let me remind you what that means. If you have a spring like this, the time period is when it goes from the top to the bottom to the top again. Or from the bottom, now we start, goes to the top and back again. Describe the displacement time relationship with an equation. Well, we know that it looks like this. A times sine for omega t, that is the displacement, like this. Now, I need to find the amplitude and omega. And from the text here, we see that the amplitude is 8 centimeter or 0.08 meter. And the time period, capital T, is 4 seconds. So I can calculate the angular frequency. We need it here. That is 2 pi divided with t. 2 pi divided with 4. That is pi divided with 2. So the relationship between the displacement and time looks like this. Amplitude, I have it in meters, 0.08 times sine 4 omega, that is pi divided by 2 t, inside the brackets like this. Okay, next question. Determine the average speed. Determine the average speed. And you know, as it oscillates forth and back, it has the high speed in the middle, and then it stands still at the top and at the bottom. So the average speed, if you want to try to do it yourself, you take a break now. The average speed is the change in distance divided with the time it takes. Now, let's see the time from the top to the bottom. The time from the top to the bottom, that is 2 amplitudes. 1 amplitude from the top to the equilibrium, and then 1 amplitude to the bottom. And how long time does it take? Well, if it takes 4 seconds from it to go down and back again, it takes 2 seconds from the top to the bottom. So the velocity has the same magnitude as the amplitude. That is 0.08 meters per second. And this is the average speed. C. The bob, or the mass, it's called a bob in your book, passes the equilibrium upwards. Determine the displacement and velocity 0.08 seconds later. Now, the bob passes the equilibrium upwards. It's going upwards. Determine the displacement and velocity 0.8 seconds later. I will show you something before we continue with this. So, there are some positions that's very easy to find. If you know that the time period is 4 seconds, 4 seconds it's here and it's going upwards, then after 2 seconds the displacement is 0. After 1 second the displacement is the amplitude, the maximum height. After 3 seconds the displacement is the negative amplitude. The velocity after 3 seconds is 0. The velocity is its maximum with negative sign after a half time period, and so on. So let's see here. The displacement and velocity. Now, after 0.08 seconds, we have to calculate it. And we need the formula for it, the formula for the displacement. 0.08 seconds later. So, x is equal to 0.08 times sine for pi divided by 2 times t. And t is 0.08. Now we have to use our calculator. The only thing I can say for sure is that it has to be smaller than the maximum value, the amplitude, or equals to, maybe, but that is 0. At another time. So let's calculate this. We use our calculator and let's write 0.08 times sine 4 pi divided by 2, and we multiply it with 0.08. So the displacement is 0.01 meter. Could be a negative sign here in front of it, then it's below the equilibrium. The velocity. What is the velocity? Then we know the differentiate function for this. So the velocity is, I write it down so we remember it, a times omega times cos for omega t, like this. So the velocity now is 0.08 times 2 pi divided by 4. Or pi divided by 2, that's okay also. Cos for omega, now I use this way to confuse you a little bit and to train you in this. So pi divided by 2 or 2 pi divided by 4, that's the same thing. Let's see what is the velocity. So we have to use our calculator. 0.8 times 2 pi divided by 4. And we multiply it with cos 4 pi divided by 2 times 0.08. And we have this answer, 0.125 with 3 significant figures, meter per seconds. Could also be a negative. If you got a negative number, it's let's see. if you have a negative number on the velocity, you don't know. No, let's see. This is the velocity. So if that is negative, the displacement can still be positive because it's going downwards. It's the direction that gives the sign. It could be negative and still going downwards. Here it changes the direction at the lowest point and going upwards. Therefore it's positive again. Okay, whoa. So thank you for today.